Hey, so now we're going to get into flocking, which is a form of autonomous behavior that actually we've talked a fair bit about over the last couple of lectures. Um, and we've actually even demonstrated some forms of flocking in a way, but not all kind of in one place. And the idea behind flocking is really that you have a few simple rules where every individual in a given population follows those rules, and as a result, a sort of emergent behavior arises out of that those individual behaviors. So while the individual has very simple things that they do, the overall group kind of behaves in what seems to be a much more orchestrated and complex way. And so flocking can allow us to do very interesting things, in particular in interactive games, that are really kind of pleasing behaviors and really kind of fun to play with. So let's kind of dive in. So here's a great link to a demonstration of how fish swim in harmony, and how, if you've seen schools of fish and they all move together, or if you've looked at herds of animals. And I think with herds, and actual like mammals on land, it's a little bit easier to understand what's going on, right? Like each individual in that group sees and has senses and has sort of a sense of itself. In fact, this is kind of a fun experiment for you guys to try the next party you go to. Human beings have this sense of personal space, right? If you've ever been somewhere where somebody doesn't really have the same sense of personal space as you do, and they are a little bit too close to you, and you kind of feel a little bit weird. And so you can actually kind of play with this idea. If you're at a party and you're talking to somebody, what you can do is you can kind of lean forward a little bit, and what they will do is they'll back up, and this is all very subconscious actually, and you can actually steer a person through a party based on kind of like leaning in, leaning back, turning a little bit. When you lean back, they'll kind of come closer to you. This is all very unconscious, right? Hopefully, I mean, it'll only happen if they don't think you're being creepy, so be aware of your behavior, obviously. But yeah, it's actually fun because you can, if you do this right, you can actually have somebody kind of stuck in a corner all of a sudden, and they're like, how did I get here? And I'm sure many of you have had that experience happen to you, where all of a sudden you're talking to somebody, and then 5 minutes later you're in some other part of the room, and you're like, how did we even get here? And so even human beings kind of react to these sort of actual forces, which are physiological. They're not actually physical things. So talk a little bit about flocking again, right? Ultimately, an individual follows a set of a few simple rules. We are going to go in the same direction as everyone else, right? So we're going to all kind of face the general same way. We're going to try to get to as close to the center as we can, which is in direct contention with the last rule, which is we don't want to bump into anybody. And also keep in mind, the way that we measure our distance to the center, the way that we measure not bumping into each other, has a massive impact on the shape of the ultimate flock that is produced. So if you can kind of think of a school of fish, tends to have a particular kind of almost like amoeba-like thing going on, whereas a flock of birds has more of a triangle, right? And so you have a little bit of a different sort of set, very subtle differences to these rules that will result in slightly different behaviors. So let's talk a little bit about these three simple rules, which are called separation, alignment, and cohesion, right? Ultimately, separation is just collision avoidance. If you know you're going to bump into somebody, you want to apply a force away from that collision. Alignment is just looking around and seeing sort of the average direction of the group and trying to match that. And you can kind of imagine that this, is if all of the objects, if you have a bunch of agents in a random assortment and orientation, and they're all trying to match each other, the ultimate vector that is set is going to be slightly random, because they're all kind of doing it in weird ways, and the physics of it, and and the forces we've talked about up till this point will sort of result in a kind of rally between and a bouncing around until boom, you get something. and then cohesion, which is this need to all be in the same place, which works in direct contention to separation, right? Because on one hand, we want to be together, on the other hand, we want to not crash into each other, and that creates a flock. And so you want to handle most likely each one of these behaviors in its own function. So you want to ensure separation, cohesion, and then you can apply forces and behaviors to that. You can have different weights applied to each one of these, so that way you can have a flock of a particular amount of cohesion, a particular amount of separation. You can play with these values. Also, you can play with the how the alignment works. You can even, this is not on this slide and in this lecture, but you can also play with things like choosing a leader based on a set of rules. You can even move the cohesion. You can, there's a lot of really fun things you can do once you have them in individual functions. You can kind of mess around with that. And let's kind of talk a little bit about each one of these functions now, and how they output and how they result in a steering force. So alignment is pretty straightforward, right? We can look around and see where everybody else is looking, and if we're not looking in that direction, we want to alter our direction ever so slightly. And so the idea here is, in this example, for example, we look at our group, and we can see that the average direction, you can either do this with a sum or an average of the vectors. Either way, it works the same. And if we look at the general direction and we compare that, right, if you recall the dot product, we can calculate the angle difference, and we can apply to that angle some kind of weight of a steering force of some kind. So ultimately with alignment, we just want to point like the same way as the rest of our neighbors. We get the average direction, we want to match the velocity to that vector, and then we calculate the steering force required to do so. And that's sort of the desired velocity, right? Ultimately is really dependent on that overall direction of the flock. So to do that, you can add all of them up and you'll get that, which is the same as taking the average if you were to take the unit vector or the average vector of them. So it depends how you want to do it ultimately, because keep in mind the magnitudes of these things don't really matter, because we're just looking at angles. We're looking at changes of orientation, not necessarily about speed. We're not trying to match the speed of the agents. We're only trying to match their overall orientation. So we just care about that dot product between the two vectors. So if it's averaged or a sum, it doesn't really matter that much. So yeah, find the sum of the forward vectors, compute the desired velocity. You can normalize it. You actually don't have to normalize it, but it doesn't matter. Then you compute the desired velocity minus the current velocity, and then you can use that as a direction, right? And apply that to use your weight of steering on that. Cohesion. The idea is to keep coherent, right? Everybody wants to be kind of in the same place. So you just calculate where the center of the objects are. This is just an average of all of the centers of all of the agents. Then we calculate a direction, and we kind of try to go in that direction in some way. And as you can see here, we can calculate the center of all of our objects, and then we want to go in that direction. We want to start to move in that direction. However, we will start to hit other forces as well as we do that, right? Like as we try to go towards it, we'll have a fighting force trying to ensure that we maintain our alignment. And we'll also have, as we'll talk about in a moment, a separation force that will try to prevent us from bumping into our peers. So the idea, right, is we want to always go towards the center, so we get the average position of all of the agents in the flock, and then we try to match our position to that vector. We want to seek the center of the flock, which is the average position that we've been talking about. And so to do that, we sum the positions, and this sum, the average of the sum, is called a centroid. And then we apply a seek force to seek this point out. Finally, separation, right? The goal is to ultimately not crash into our neighbors. right? If you have a physics engine running on top of this, you will bump into each other. The physics will apply, I believe, in the code that you're going to write, and the examples you do, you're not going to have that. So you kind of have to. It'll be pure forces, but in reality, if the two agents bump into each other, they'll bounce off. But you don't want that. You want to avoid it. You want to ensure kind of this invisible bubble around each individual. And so the separation force will kind of ensure or kind of promote that separation. And so the idea here is, as we've talked about collision detection before, or collision of obstacle avoidance, I should say, right? You just determine, oh, we're going to hit something, and if so, we steer away. And once we steer away, then the other forces again come into play, right? We steer away, but then we want to get aligned, but then we want to kind of go back and cohere and seek out that center point. And so the balance of all these forces will ultimately result in a flock behaving in a sort of consistent or coherent manner. And there's a couple of ways to do separation. We've talked about this in previous lectures. You either want to look at the closest neighbor, right? So what you do is you would then find the closest neighbor, and if it's too close, then you flee. Now, this is, it's important to note, by the way, what does too close mean? You have to define that, right? So you can use a heuristic like we've done in the past, which is you take the distance, you divide it over one, you divide one by it, and as you get closer and closer, that heuristic goes up. You can have a minimum bias of it. You can do a lot of things like that, or you can just have a linear, as the distance gets below 1 or below 2, you can scale it and have kind of like, as you get closer, the force becomes stronger in a linear way. Many different ways to do this, but ultimately the result is the same. Or as I like to say, lots of ways to play, one way to win. The nice thing about you only looking at one neighbor is it's simpler to program, obviously. You just look at the one that's closest and great. It's actually not simpler to program because you have to determine which one's closest and then apply the force to that, but it is less performance. And it looks okay when there's not that many objects in your flock. When there's not that many things to consider and the likelihood of being completely surrounded is relatively low, then the checking only one at a time is okay. The downside is that the steering force, if you're only considering one object, say you've got two objects, one to your right, one to your left, two agents, and you're like, okay, well this one's closer just by a little bit, and then you steer and you go straight into your left neighbor because you're not looking to your left. It also can create a bit of a jitter, right? So you steer to the left, and then the left is too close, and you steer to the right, and it's just kind of this jitter. You're constantly going back and forth. But had you considered both of them at the same time, the ultimate steering force would say, you know what, we're like slightly closer to this one, so like let's just nudge to the left, not all the way. And so looking at multiple neighbors can be much better when you're going to be surrounded and there's many objects. Those are kind of the downsides of only looking at one neighbor at a time. So the alternative is let's look at all of our neighbors, or let's look at all of our neighbors that are within a given distance, or all of our neighbors within a given distance up to a certain number, which we'll talk about in a minute. But ultimately, you're looking at multiple neighbors within a certain range, and you apply a flee force for each one of them, or at least you determine what the flee force would be, or the directionality of that flee force, and then apply a weight to that directionality, as if it's one kind of averaged flee force. And so the pros of this is that it looks way better, right? As we said, if you have, for the example of having two agents, one to your right and one to your left, say you're just a smidge closer to the one on the right, then your flee force will be just a smidge to the left, because the rest of the left force will be clobbered out by the flee force from your left to go to the right. So this one's saying go this way, this one's saying go that way, this one's saying go this way a little bit more, and so you get you kind of a nudge to the left versus a full-on swing to the left. The downside is that it's arguable that it's easier to code or it's more performance. It's a little bit hard to kind of say, right? Because in the first one, when you're only looking at one, well, you only have to look at one, so you only have to do one set of calculations, but you do have to determine which one's closest. So you do have to run through that code of determining, okay, is this one, this one, this one, this one. This one's the closest. Let's apply to that. when you have multiple neighbors that you're considering, you do have to kind of create a set of objects that are within the boundary, and then figure out which ones are closest, and then apply these rules to each one iteratively. And that is a little bit more complicated to program, not significantly more, but it is significantly more computationally expensive, especially as you scale out to many, many objects in your swarm. So if you've got 1,000 objects, each one of those objects, if it's considering the collision with its neighbors with each one of those objects, is looking at 999 other objects. Now say you're limiting that down to a certain limit of, like, say, a maximum of 10 objects that are near. For 1,000, each object is doing potentially 10 calculations of this, and also determining against the 1,000. And so you can hear that, like, this scales up, with the number of objects pretty rapidly. So testing this is a lot of fun. So you should test your project, right, with different weights, which should be in the inspector to make it a little bit easier to understand how to tweak things. And we can assign kind of the separation alignment weights 0 initially, and then you can kind of set these cohesion values to 20 for, like, these are just example numbers, but the idea here is to check one force at a time. So check if all your cohesion is working. If it is, then set everything to 0 and then try alignment. And if that's working, then check your separation. And if they're all working, then you have a pretty high likelihood of them all working together. And so sometimes, so what you can do is sort of separate each force and check one at a time, and then check two at a time, right? These two, and these two, and then check all three of them together and see. And that way you can kind of tweak the values and get to a place where you're pretty happy. So let's talk a little bit about the efficiency, the performance, and how realistic is this really, and how do we tweak the simulation to get to those parameters. And so for a single flock, right, the average position and the average direction is the same for each member. All right, this is because we're trying to have everybody in the same place, and we're trying to have them all point in the same direction. So should we have every single one of the members, agents, calculate this average position and direction? Well, no. Right? The idea here is that, in theory, we could do this once, and then they all can access it, and that way you save a lot of performance. Right? Going back to the example of 1,000 agents in a swarm, each one of those agents would have to calculate the average position, average direction. Now, if you've got like 10 objects, it's not a really big deal, but if you've got 1,000 or more, imagine you apply this to, say, a particle system with even, tens of thousands, if not hundreds of thousands of elements. You probably don't, you want to find ways to share calculations across all the different elements of that swarm. And so, yeah, one thing we can very easily do is calculate the average position on a given frame, the average direction on a given frame, and then provide each agent with access to that in a way such that they don't have to individually calculate that. Now, there is some nuance here, because as you go through your list of agents, these values will affect the swarm, and as a result, change the position, change the direction on average. So, this brings up a problem, right? But in theory, what we want to do is we want to operate in frames, right? And the state of the scene should be the same for each individual agent in our swarm. And so you'll find often, if you don't do this, and if you don't set a value up front that everything works off of, then now this agent and this other agent will work off of two different positions and two different orientations on average, and you may have some unintentional effects. Now, sometimes this is good, right? But often it's not good. Often you'll just get jitter because these values are changing, and in particular we're talking about small numbers, and as a result of that, you'll have a lot of kind of boundary conditions, and things will kind of pop back and forth. So it's much better to just run against a existing state, kind of like freeze the state, calculate the updates for each individual objects, then update the whole state all at once versus doing it by one at a time. Basically, the idea of doing it in a stochastic way versus a batch or general way. And so how do we make this a little bit better? We talked about weights. So should some things be more influential? We can have separate weights for all of these different forces, like separation, alignment, and cohesion should all have different weights. You can kind of imagine, say, separation is probably more important than cohesion, right? Because as the balance between cohesion and separation kind of swing, with cohesion, we all want to stick together. With separation, we all want to stay apart. And so if your cohesion force is stronger than your separation, we're going to be bumping up against each other a lot more than we're going to stay apart. And so you do want to think about that, the weighting of what's more important than the other. And this is also kind of fits into what about behavior, right? What about eating food or whatever? So making sure that we kind of prioritize the steering forces according not just to the flocking behavior, but the other behaviors in your simulation. And you can also kind of think about turning these things on and off. Like, for example, if you've ever watched a school of fish being like penetrated by a predator, and often the school will split and split into two groups because running away from a predator is much more important than sticking together as a school. While schooling is for the intended purpose of staying safe in numbers, that is a second priority to staying alive, ultimately. So, that's why sometimes you turn off things. You can just entirely turn off flocking or turn off food stuff, seeking food based on the other environmental factors in your simulation. This is a really important thing to kind of note, and I've talked about this in our lectures a number of times now, where in a game or in a simulation environment, you are omnipotent, right? Each object can be omnipotent by association, right? The object is given information by our simulation, operates on that information, but we know everything. We know where every other object is. We know everything about the environment. But that's not how reality is, right? Like, I can't see what's behind me. Maybe I can infer it, but I don't know. And same thing with animals. And you can see here a couple of examples, right? Human beings have stereo vision in a particular field of view, and outside of that view, it's mono. And then owls have the slightly more constrained, and pigeons have very wide field of view in total, but very, very narrow stereo vision. The difference between stereo and mono is that in stereo you can sense depth, and human beings are able, as like if I hold my cup here, I can sense how far away it is. I can see where my hands are if I have if I can sense depth with two eyes. But if I'm only if I only have one eye, my depth perception goes dramatically down in quality. And while you can still sort of infer how far things are, you're no longer using stereo vision to do so. It's no longer a parallax effect. It's more based on things like optic flow, meaning when objects come towards you and they get bigger in a particular way, right? The optic flow indicates their speed and depth. If you know something about the object, you know how big a cup is, and it gets closer to you and it's getting bigger in a particular way, you can kind of infer where it is. This is, by the way, how flies see the world and how they can navigate. They don't actually have stereo vision. They operate depth perception based on optic flow, which is also very important when you're moving very fast. Depth perception doesn't work very well when you're going extremely fast, and so everything's based on optic flow, which is why flies have developed that technique. And so you have to kind of consider that, where if you want to simulate these agents in a more advanced and more realistic way, you only want to consider objects or consider other agents within their field of view. You also want to have a maximum limit of agents that they can consider, because you're limited. You can't, as a human being or as an animal, you can't consider every other object in your environment. You have to focus on a certain limit, and most birds can pay attention to about 6 or 7 things simultaneously, and I think human beings have a similar limit. And yeah, what's really cool about this is that it creates a much more realistic thing. It creates an ability for flocks to kind of separate and do more interesting behaviors. So on the optimization side, just to kind of recap, right, we can pre-compute some shared values. This will reduce the amount of performance required to do a lot of the flocking stuff. We can variably update, like we don't actually have to update things every single frame. This will assist with performance, but will also affect the behavior and the quality of the algorithm. So it's kind of a balance between the two, but you can sort of think about this, instead of doing it every single frame, perhaps you do it in a particular time step. So instead of every frame, you do it every 100 milliseconds. Will that work? It will. All right, but you will have 100 milliseconds of time where updates are not being applied. And so there is kind of this balance of, okay, how do we keep this from becoming jittery? Another thing we can do is what's called spatial partitioning, which we haven't talked about too much yet, but we have done a little bit of, obviously, collision detection. And the idea here is, well, if I can take the world and I can split it up into quadrants or into kind of cells, where there's a maximum number of objects in a particular cell. So you can say like one object per cell, right? And in a cell you can have other cells, and maximum of 2 cells per cell, and blah blah blah, like a binary tree. Then that way you can say, okay, I want a cell, this object is in this cell, and go up a sufficient number of levels, and then give me the number of objects that are closest to me. So instead of having to look at all 1,000 objects, I can only look at this sort of tree that I'm going through, and getting with limited number of steps that. But we haven't talked about spatial partitioning or spatial organization trees too much up until this point. And another thing about performance in general is just reusing data structures, or reusing values. So like creating vectors and squashing them, especially in a dynamic language like C#, is a lot of performance, right? Allocating memory and then deallocating it and so on. It's a big drain on performance. So using something that's permanent, like even like a global temporary variable. So having a vector3 temp that you use instead of allocating a new one actually can have a significant performance improvement on your program. And obviously, if you do that as a member variable, same kind of concept. But be aware that if you're doing like a nested for loop with like 2 nested for loops, and then inside of there you're creating 3 vectors every single time, you're doing that. If you have 1,000 agents, you're doing that 1,000,000 times. You're creating 1,000,000, and that can add up with allocation. So yeah, that's about it for flocking. And now you know pretty much everything you need to know to have a number of agents behave in sort of a cohesive way. And excited to see what you guys do with it.